Hey everyone! Welcome to AirWise Academy, your trusted source for EASA Part-66 learning. Today, we're starting one of the most important modules in the entire syllabus, Module 3, Electrical Fundamentals. Think of this as the essential language of aircraft systems. Before we can understand how complex avionics, navigation, or starting systems work, we must first understand the basic principles of electricity that make them all possible. In this module, we'll build that foundation from the ground up. We'll start with the core theory of atoms and electrons, understand how static electricity works, and learn the key terms every engineer must know. We'll then explore how electricity is generated and stored in DC sources, like batteries. We'll spend significant time mastering the fundamental laws that govern all electrical circuits, Ohm's law and Kirchhoff's laws, and apply them to understand resistance, power, and capacitance. From there, we'll get into the fascinating world of magnetism and induction, which is the absolute heart of how generators and motors operate. Finally, we'll progress to AC systems, covering everything from theory to the transformers and generators that are vital for aircraft operation. This module is the bedrock of your knowledge, so let's dive in and build a strong electrical foundation together. Let's take a closer look at the journey ahead in Module 3. Submodule 1, Electron Theory, is our true starting point, where we'll explore the atomic structure and how the behavior of electrons in atoms defines the very nature of electrical charge. This leads directly into Submodule 2, Static Electricity, where we'll study these charges at rest, learning the laws that govern how they attract and repel, which is crucial for understanding phenomena like triboelectric charging on aircraft. Before we can build anything, we need the right vocabulary, which is exactly what Submodule 3, Electrical Terminology, provides, solidifying our understanding of fundamental terms like voltage, current, and resistance. With those terms defined, Submodule 4, Generation of Electricity, shows us the practical ways to actually create this electrical energy, from chemical action in batteries to the magnetic induction that powers entire aircraft systems. A key source of that power is covered in Submodule 5, DC Sources, where we'll dive into the construction, chemistry, and series/parallel configurations of aircraft batteries, the vital reservoirs of DC power. Once we have a source, we need to understand how the energy flows through Submodule 6, DC Circuits, by mastering the absolute non-negotiable laws of circuit analysis, Ohm's law and Kirchhoff's laws. Within those circuits, we need to control the flow of current, which is the purpose of the components we study in Submodule 7, Resistance, learning to calculate total resistance and understand the practical use of devices like potentiometers. All that current flow through a resistance leads to Submodule 8, Power, where we learn how electrical energy is converted into heat or work and how to calculate the dissipation that dictates component sizing. Finally, we'll cap off Part 1 with Submodule 9, Capacitance, learning how capacitors store and release electrical energy in a circuit, a fundamental concept for timing, filtering, and energy storage applications. Part 2 of our module is where we harness the fundamentals to understand the devices that make modern aviation possible. We begin with Submodule 10, Magnetism, establishing the principles of magnetic fields and electromagnetism, which are the invisible forces that enable generators and motors to function. Those magnetic principles are put into motion in Submodule 11, Inductance, where we discover Faraday's and Lenz's laws, explaining how a changing magnetic field can induce a voltage in a conductor, the basic principle of all generators. This knowledge allows us to understand Submodule 12, DC motors and generators, in depth, breaking down their construction and how they convert between mechanical and electrical energy, which is essential for aircraft starting and power generation. The modern aircraft primarily runs on alternating current, which is introduced in Submodule 13, AC Theory, where we learn to characterize sinusoidal waveforms using values like RMS and frequency. The behavior of AC circuits is more complex than DC, which is why Submodule 14, R, C, and L circuits, is critical as it teaches us how resistors, capacitors, and inductors affect the phase relationship between voltage and current and how to calculate impedance. A vital component in AC systems is covered in Submodule 15, Transformers, which allows us to step voltages up or down efficiently with minimal losses, a key process in aircraft power distribution. To ensure clean power for sensitive avionics, Submodule 16, Filters, shows us how circuits can be designed to block or pass specific frequency ranges, protecting critical systems from electrical noise. The primary source of aircraft AC power is the generator, studied in Submodule 17, AC generators, where we'll compare different types, like revolving field alternators and their three-phase star and delta connections. We end our journey with Submodule 18, AC motors, exploring the construction and principles of induction and synchronous motors, which are used in various systems across the aircraft for their reliability and control. First, let's break down the 3 knowledge levels that EASA uses to define the depth of understanding required for each module in Part-66 training, starting with Level 1. This is your entry-level understanding. At this stage, the technician has general awareness and basic knowledge. They are expected to perform simple procedures, but always under supervision. Think of it like learning the tools of the trade and recognizing parts, but not making decisions yet. Moving on to Level 2, here, the trainee is expected to have a deeper understanding. They should be able to explain system functions and understand how components work together. At this level, they can carry out maintenance tasks, but usually with some form of technical guidance or reference to manuals. Finally, we have Level 3, the most advanced level. This is where a trainee becomes highly proficient. At Level 3, the individual should be able to troubleshoot issues, perform detailed inspections, and most importantly, make independent technical decisions. This level is crucial for those who will certify that an aircraft is safe to fly. So understanding these levels is key, not just for passing the exams, but for knowing what's expected of you at different stages of your aviation engineering career. Now, let's zoom in on our first submodule, Electron Theory. This is where it all begins. We need to start incredibly small, at the atomic level. We'll look at the structure of atoms, molecules, and ions to understand how the movement of electrons creates electrical charge. Then we'll see how this fundamental knowledge explains why materials behave so differently. We'll classify them into 3 key categories: conductors, which allow easy flow of electricity, insulators, which resist it, and semiconductors, which form the basis of all modern electronics. This might seem basic, but this knowledge is the absolute foundation for everything else in this module. It's the essential first step to understanding how electricity works in an aircraft. For both B1 and B2 licensed engineers, the required knowledge level for electron theory is Level 1. At this level, you need a general awareness and basic knowledge. Now, let's get started. Before we dive into circuits and components, let's ask the fundamental questions. How does energy travel throughout an aircraft? What exactly creates electric current and EMF, or electromotive force? And most importantly, what's powering those critical aircraft systems like landing lights, fuel pumps, and flight controls? The answer lies in understanding the basic building blocks of matter: electrons, protons, and neutrons. Get this foundation solid, and the rest of electrical fundamentals will become much clearer. First, let's define matter. Matter is anything that has both mass and volume. Essentially, it's the substance that makes up all physical objects around us. Now, it's crucial to differentiate between mass and weight. Mass refers to the actual amount of matter contained within an object. It's a fundamental property of the object itself. Weight, on the other hand, is the force exerted on that mass due to gravity. Therefore, an object's weight can change depending on the gravitational field it's in, while its mass remains constant. Finally, for those of us dedicated to aviation, we will focus on the 3 states of matter most relevant to our work: solids, liquids, and gases. Understanding these states is crucial for comprehending the behavior of various components and systems in aircraft. Now that we understand the basic concept of matter, let's delve into the fundamental substances that compose it: elements and compounds. Elements are the purest form of matter. An element is a substance that cannot be broken down into simpler substances by chemical means. Think of them as the building blocks of everything else. Examples of elements you'll encounter frequently in aircraft maintenance include copper, Cu, used extensively in wiring, gold, Au, often used for corrosion-resistant plating, oxygen, O, essential for combustion engines, and iron, Fe, a primary component of many structural materials. Compounds, conversely, are formed when 2 or more elements chemically combine. Unlike elements, compounds can be broken down into their constituent elements through chemical processes. A common example is water, H2O. As you can see, it's a compound made up of the elements hydrogen and oxygen chemically bonded together. Moving on, let's discuss molecules, the smallest units of a compound that still retain the compound's properties. A molecule is the smallest particle of a compound that can exist independently while still possessing the characteristic properties of that compound. Important note: if you were to break down a molecule further into its individual atoms, it would lose the defining characteristics of the original compound. For instance, a single H2O molecule is the absolute smallest amount of water you can have. Any further division breaks it down into hydrogen and oxygen atoms, which individually don't behave like water anymore. As shown in the figure in this slide, you can see the depiction of a molecule of water. Let's zoom in on the atom. It's comprised of 3 fundamental particles: protons, which carry a positive charge and reside in the nucleus; neutrons, which are electrically neutral and also in the nucleus and add mass to the atom; and electrons, which carry a negative charge and orbit the nucleus. Here's the key takeaway: the number of protons defines the element. Hydrogen has 1 proton, helium has 2, and so on. The electron's ability to move between atoms is what enables electric current to flow. Remember the charge relationships: opposites attract, positives and negatives want to be together. This shows a simplified model of an atom. In reality, electron orbits are much more complex. It's important to know that these atoms and molecules are never still. The kinetic theory of matter states they are in constant motion. This motion explains why things expand when they get hot. The particles are vibrating faster and need more space, and contract when they cool down. This principle is vital for understanding everything from terminal expansion and connectors to fluid dynamics, even though water, famously, is an exception to this rule when it freezes. Let's examine the 3 subatomic particles in detail. At the center of the atom is the nucleus. This dense core contains protons, which are positively charged, and neutrons, which have no charge. A proton and a neutron have approximately the same, relatively large mass. Orbiting this nucleus are electrons. These are negatively charged particles with a very small mass. A proton is over 1,800 times heavier. This structure defines their roles. Because electrons are on the distant periphery, they are the particles that change during chemical reactions. The massive nucleus, containing the protons and neutrons, determines the atom's overall mass, as the weight of electrons is negligible. The balance of charge is critical. An atom is electrically neutral when the number of protons in the nucleus equals the number of electrons orbiting it. We can see this in examples. Hydrogen, shown in the first figure, is the simplest atom with 1 proton and 1 electron. A more complex atom, like oxygen, in the second figure, has a nucleus of 8 protons and 8 neutrons, balanced by 8 electrons arranged in orbiting shells. Now, let's discuss how electrons are organized within the atom. Each electron requires a specific amount of energy to maintain its orbit around the nucleus. This is known as its energy level. These energy levels are not random. Electrons can only exist at specific, definite levels. For convenience, we group these closely spaced levels into what we call electron shells. The maximum number of electrons any shell can hold is determined by the formula 2 times n squared, where n is the shell number. This means the first shell, closest to the nucleus, can hold 2 electrons. The second shell can hold 8, and the third can hold 18. These shells fill from the one closest to the nucleus outward, as it is the lowest energy level. A key point is that an inner shell does not need to be completely filled before electrons begin to populate the next higher energy level. To know the exact electron configuration for any element, you must consult the periodic table. An atom's ability to bond with others is defined by its valence, which is the number of chemical bonds it can form. This property is determined by the electrons in the outermost shell of the atom. These crucial electrons are called valence electrons, and they are solely responsible for forming bonds with other atoms. Ionization is the process that creates charged atoms, known as ions. If an atom loses a valence electron, it will have more protons than electrons, resulting in a net positive charge. This is called a positive ion or a cation. Conversely, if an atom gains an extra electron, it becomes negatively charged and is called a negative ion or an anion. Remember, a standard neutral atom has an equal number of protons and electrons. In solid materials, the story of valence electrons continues. While inner shell electrons are tightly bound to the nucleus, valence electrons in the outermost shell are much more loosely bound. Because of their distance and weaker attraction, they are often called free electrons. They can be easily knocked loose from their atom. Once free, they can move throughout the material. This organized drift or flow of free electrons is what we know as an electric current in a circuit. The behavior of valence electrons doesn't just define chemical properties, it also defines electrical properties. An atom's ability to gain or lose electrons is the fundamental factor that allows us to categorize all materials based on their ability to conduct electricity. These 3 categories are conductors, semiconductors, and insulators. Let's discuss conductors. These are materials such as gold, copper, and silver that are excellent conductors of electric current. This exceptional conductivity stems from their atomic structure. The atoms in these materials have loosely bound electrons in their outer orbit. When energy, in the form of heat or an electric field, is applied, it causes these valence electrons to break free from their atoms. This results in a large number of free electrons available to move through the material. For instance, a copper atom has only 1 valence electron. Because this bond is so weak, billions of these electrons are free to drift even at room temperature, making copper an ideal conductor. On the opposite end of the spectrum are insulators, such as glass, ceramic, and plastic. The atoms of these materials hold onto their electrons very tightly. They do not readily produce free electrons. This absence of charge carriers prevents current from flowing. If an extremely strong electrical field is applied, it can forcibly dislodge electrons in an event called dielectric breakdown, which typically shatters or otherwise permanently damages the insulator. Occupying the middle ground are semiconductors. As the name implies, their electrical properties are neither those of a good conductor nor a good insulator. The most widely used semiconductor materials are silicon and germanium. Their unique and controllable conductive properties are the foundation of all modern electronics. For a much more detailed explanation of how they work, you will continue your study in Module 04, Electronic Fundamentals. And that brings us to the end of this session for today. Now, let's warm up with a few questions to review what we've learned. Now let's get started with question 1. What is the key difference between mass and weight? A. Mass is a measure of volume, while weight is a measure of gravity's pull. B. Mass is constant, while weight depends on gravitational force. C. Weight is the amount of matter, while mass is the force acting on that matter. The correct choice is B. Mass is constant, while weight depends on gravitational force. Here's why this is crucial for an aircraft technician. The mass of a component, like a battery, remains the same whether it's in a hangar on Earth, being weighed during maintenance, or in flight. However, its weight, the force exerted on the scales, would be different on the Moon because of the weaker gravity. Understanding this distinction is fundamental for calculations involving force and for following technical data that often specifies mass, not weight. Question 2. According to the kinetic theory of matter, why does most matter expand when heated? A. The atoms gain more protons and neutrons, increasing their size. B. The particles vibrate more and require more space. C. The atomic bonds break down, allowing atoms to spread out. The correct answer is B. The particles vibrate more and require more space. This is a perfect application of the kinetic theory. When you add heat energy, you transfer that energy to the atoms and molecules, causing them to vibrate or move faster. This increased motion means each particle needs slightly more room to move, causing the entire material to expand. This is a critical concept in aviation. We see its effects in things like thermal expansion in engine components, the need for expansion gaps in airframe structures, and even in the operation of certain temperature-sensing instruments. Question 3. What is the defining characteristic of an element? A. It cannot be reduced to a simpler form by chemical means. B. It is a chemical combination of two or more atoms. C. It always has a neutral electrical charge. The correct answer is A. An element is a fundamental substance that cannot be broken down into a different, simpler form through chemical reactions. Option A describes a compound, and option C is not always true, as elements can become ions. Question 4. What is a positive ion, cation, formed by? A. Gaining an extra proton. B. Losing one or more electrons. C. Gaining one or more neutrons. The correct answer is B. A positive ion is formed when an atom loses one or more of its negatively charged electrons, resulting in a net positive charge. The number of protons in the nucleus does not change during ordinary chemical reactions. Question 5. What is the primary function of free electrons in a conductor? A. To determine the atomic mass of the material. B. To form strong chemical bonds between atoms. C. To flow and constitute an electric current. The answer is C. Free electrons are valence electrons that are loosely bound and can be easily dislodged. Their movement from atom to atom is what we define as an electric current in a circuit. Question 6. Which material is typically classified as a semiconductor? A. Silver, Ag. B. Glass, C. Silicon, Si. The answer is C. Silicon. Semiconductors like silicon and germanium have electrical properties that fall between those of conductors, like silver, and insulators, like glass. They are the fundamental materials used in modern electronics. That's all for today's lesson. If you found this video helpful, please give it a thumbs up and consider subscribing to AirWise Academy for more aviation knowledge. We'd love to hear your thoughts or questions in the comments below. Turn on notifications so you won't miss our upcoming videos. Until next time, blue skies and happy learning!